Hey, good afternoon, everyone. I'm here with Dr. Alan Rose from Corrdesa. Um, just to let everyone know, if you can pop your questions either in the Q&A at the top or the chat, and Alan will answer them towards the end. We're anticipating 45 minutes of presentation with 15 minutes Q&A at the end, roughly. Okay. Before I hand over to Alan, I'll give him a quick introduction. Alan's got BSc from Manchester. His PhD is from Sheffield. He has spent 30 years of his life in computer simulation to help shorten design, get product to market sooner. The markets that Alan's been involved with has been gas turbines, nuclear, aerospace, and automotive. And with that, Alan, or Dr. Alan, I'll hand over to you.
Okay, thank you very much. You can hear me okay, Carl?
Yes.
Okay, excellent. So let me get this presentation started. Okay, so you can see my screen?
Yes.
All right, then. Okay. So what I wanted to do, so I'm from Corrdesa, based in the USA, and that's me on the left. And my background is computer-aided engineering, so I've done a lot of computational fluid dynamics, whether it's in nuclear, aerospace, or whatever. And we started Corrdesa in 2011, where we have with Keith, the co-founder. So his expertise is in coatings, materials, reduction of hazardous materials. We've worked a lot with the Department of Defense on corrosion panel advisory boards to look at strategies for reducing content of chromates and so on. That's his expertise. And then another one of our partners, Siva Palani. He's from Airbus, Nissan, so aerospace, automotive experience. A lot of experience in electrochemistry and the simulation of electrochemical processes, whether it's plating, electroplating, electrochemical machining, or today we're going to talk about corrosion. So that's a bit of a background of our company. So what I want to do today is we've developed corrosion prediction methodologies and software tools, as well as hardware and various coating repair processes. And I want to try and cherry pick some of these learning experiences, share with you. Hopefully some of it will be new and interesting information. And you can see how we have been deploying corrosion prediction tools and also helping other OEMs and supply chain to deploy the same tools in order to comply with standards coming down from their customer, Air Force, Navy, or whatever. We'll talk a little bit about standards. There's a lot to learn from standards. They align very well with proprietary guidelines. So, and the MIL standards in the US, they're free. So there's a lot of information in there. On the other side as well, we have sustainment and hardware, and how do we actually repair some of these coatings that we've specified. Thought that might be interesting on how we're doing on-asset repair. So this is our world, and we have experience in the sustainment side. So I'll talk a little bit more about these little machines here that look like little robots. Essentially, they're mobile machines. You can do electroplating with them. They have tools that are non-drip, and you can take them right up to the asset, whether it's a smaller version in a submarine or on an aircraft, or bring it right up to the plane. But working with our customers, such as the Air Force and Navy, we see a lot of issues. So it's great to see these actual challenges that our customers have and help them try and mediate those corrosion issues. But many of the issues could be avoided by a better choice of design and materials. So we developed over the last few years software tools, and we've integrated these capabilities into commercial CAD tools in order to assess and look at corrosion risk very early on in the design process. Point out these other aspects as well. When we started doing this, we realized, unlike if you're doing computational fluid dynamics, a lot of those properties are available in the software, in the CFD software. So, that path has been beaten already. When it came to corrosion, there's very little data to use in our models. So we spent quite a while, we created a panel where we worked with, like Boeing, Safran, some academic people and federal agencies, and came up with a data acquisition protocol to ensure that the data was gathered in a consistent and robust way. So I'll come to that in more detail later on. So we do a lot of data acquisition. We're very familiar with the testing. We can simulate these testing environments as well. And of course, people work in different environments and also have different missions for their assets. So we've incorporated capability to look at the impact of different environments and different missions. So it's a big problem in aerospace. It's a readiness problem. If you have an aircraft on the ground, it can cost you a lot of money, whether you're trying to fly your people off to sunny Spain or it's a jet fighter that needs to get in the air at a moment's notice in terms of mission readiness. Obviously, civilian or military has an impact on structural integrity and safety. And, presently we rely a lot on very prescriptive standards and a lot of inspection. And I think there's a lot of room for incorporating, prediction methodology into condition-based maintenance. It's relevant also to automotive. We're getting a lot of traction now in the automotive area. They cover their cost in the warranty, essentially. So obviously, if they can reduce corrosion costs, that would have an impact on what they spend out in their warranty. And there's always an interest in reducing, in increasing the platform longevity, because they like to use the same platform for different models of cars. And again, safety and degradation of materials. And there's new problems with EV architectures as well, stray currents and such. So the key message here really is, although we worked in aerospace first and it's felt the impact first, or they kind of started doing something about it in terms of, what can we do out of software and prediction, the physics are universal. So in aerospace, cost of corrosion is huge. I mean, internationally, across all industries, it's huge. And probably teaching you to suck eggs here, you're probably very familiar with these numbers. A couple of things I will pick out is in the FAA, in a report said 23% of their failures trace back to corrosion-related issues, which is, I find, quite a large number. Another thing as well, when people are always saying, why did this happen? Why was this specified in such a way in the design? 70% of your sustainment costs are locked in by the decisions you make in design. So you need to have the best data you can and do the best job you can in design, because you have to live with them for a long time. Certainly in the aircraft industry and in the military, these platforms last for decades. And another thing as well is the coating legislation, it changes over time. So when we come back into depot maintenance and you want to recoat with cadmium, you might not be allowed to do that. Now you have to recoat with something else, something that's less hazardous, which has to be tested and qualified, and simulation can speed up that process. It takes more than 10 years to deploy new coatings. Another thing as well, like I've mentioned, and it's the same with the automotive, studies have shown that the cost of corrosion can be eliminated upfront in design, and you need better tools and deploy better data. So there's parallels in automotive, and we're beginning to beta track in the automotive side as well now. Maintenance cost, good fraction of maintenance cost in cars is due to corrosion. They have the same issues as well in terms of changing legislation, meeting REACH, ROSE, OSHA kind of EPA compliance requirements. And there's some new issues coming now with battery casings and connectors and cooling systems for electric vehicles. So, why are we seeing this now? Obviously, in automotive design, They're using very exotic materials, just like they use in aerospace. We're always chasing, power, performance, and lightweighting. I have to keep safety in mind, of course. But it's important to reduce the vehicle weight. And also with EVs, the batteries are so heavy. The more we can make use of light alloys and composites, then the lighter you could make your product. But this introduces a lot of complexities in terms of protecting for corrosion, designing those fixture systems in such a way that you don't increase the galvanic corrosion risk. So all these materials expand and corrode differently, they fatigue differently. So testing is the traditional way and is a requirement of physical testing. But what we've done is developed some software methodologies and tool techniques that can simulate these tests, simulate these materials in the field, and can reduce that whole process. And I'll introduce some of them to you shortly. There's always this push for replacing hazardous materials. If you've been working with cadmium or chrome for decades and then told to change, that's a lot of work and qualification that you have to fit in a very short time frame compared to the past, 40 years or so. So there is definitely a big push. You'll have heard of, digital transformation. Large enterprises are looking at how they can, you've heard of digital twins and such, and how can they simulate more so they can do things quicker, more upfront, shift left. Physical testing is costly, and even if it's accelerated testing, it still takes a lot of time. So I'm going to show you some of the things that we've done with the simulation tools that we've developed. So often testing happens too late, rules of thumbs don't scale. And another thing about simulation as well, because you're set up digitally, there's a good auditable trail that you can create, so you can look at exactly what you've done. You can manage all of this process. You've not got your data scattered around in spreadsheets and so on. So you connect your material choices, and the corrosion risk is connected to the design and travels with that design. So we'll avoid designers flying blind. So here's an example. So we started off, there are many mechanisms of corrosion. We started off with galvanic corrosion simulation. The Navy put out a bid, a request actually, for information. Can we model galvanic corrosion? Just like thermal analysis, stress analysis, that was the idea. And the reason they chose that is just, eating the proverbial elephant. It's like, well, what hits us most? And in teardown studies on the FA-18 from Top Gun, they showed that 8% of the structural fatigue issues were related to galvanic corrosion. So if you lift the composite skin off the airframe here, you got very nasty corrosion interaction between the composite skin, the aluminum alloys, and the fastener systems as well. So this led to a real readiness issue, as low as 50%. What's readiness? That means at any point in time, only half of my fleet are able to go and fight. So obviously that was a big event, and there's lots of other issues that cause and lower the readiness, but the corrosion was certainly one of them. And it's not surprising when you look at this, the hostile environments that the Navy had to cope with is kind of mind-boggling, really. Well, they dump tons of seawater onto these helicopters and planes. So looking closely, this is the corrosion that you can get, and the impact is you have to repair it. So what they do is remove the corrosion, and then there's various different ways of putting a bushing in there to bring back that tolerance. They freeze them in liquid nitrogen, or they force mate them in this cold forming process. Either way, it takes labor, it takes time. And when you consider that there are more than 20,000 fasteners in the center barrel of an F-18. That could be a very expensive process. So clearly they needed to deal with that. Now the F-18 is quite an old asset, but even the newer assets, there've been issues. There's issues with F-35, but on the F-22, there's quite a well-known issue, and that was a gap filler that they chose on the wing panels. And this conductive gap filler, which was chosen for obviously, kind of low observable type of issues, had unexpected impact in the accelerated galvanic corrosion. And just to fix that one problem cost more than $228 million. So clearly, if you have tools up front, you can look at the impact of these choices of materials, see what the impact is on your total design. We've done this retrospectively, and in the software that we developed, this would have flagged up like a Christmas tree, and it would have been a non-event. We would have dealt with it and worked in an alternative material. So, talk about the corrosion prevention control planning. So, I'm becoming more familiar with the standards here in the UK, but in the US for military acquisition, there's a requirement for corrosion prevention control planning. It's covered by this MIL standard 15680. All the standards are publicly available. And the key points of this, I'm not going to get into the details of this particular standard, but I think of it as a bit of an umbrella type standard. It's interesting to note that it is law. It comes down from US code, and it is law to have this corrosion office in place. And in order to meet the law, they create the policies, these DoD instructions, and then from these DoD instructions into the hands of the engineers, they have the MIL standards to follow in order to trickle back up and meet the requirements of the law. So that's quite a big kind of a compliance issue for the OEMs, and they have to show and substantiate what measures they've taken to assess any risk in these systems and why they've chosen those particular materials or coatings. So we'll drill down a little bit now. There's a multitude of MIL standards. There'll be the equivalents, surely, in the UK and Europe. The MIL standard 1568 calls out and refers to this 889, and that's for galvanic corrosion, which is what we're going to talk about in more detail now. So it's a couple of points to note. These are the standards. The 1568, in there, I pull a few clauses, and it says modeling and validation testing shall, it's not may, it shall be performed to identify corrosion-prone locations. If it's a new system, how are you going to do this priori? You can't extrapolate all the time successfully from your previous experience. And it says testing. So in my mind, computational fluid dynamics, computer-aided engineering, to me, testing could be physical testing, which has its own limitations, and also virtual testing, which also has its limitations. And then in there's a requirement to look at galvanically dissimilar materials and coatings. And the big change is the MIL standard for galvanically dissimilar materials used to be a potential series, but now they've changed the way that they look at it. It's a requirement that you use polarization curves. So if you're familiar with polarization curves, we'll talk a little bit about it in a minute. But you have to use polarization data. The reason being, it's more accurate in this way. To change the galvanic dissimilar materials was the title, and now it's called galvanically compatibility of electrically conductive materials. So this is another change because it's not just like, metals and alloys, coatings, but it really matters. You've got to be cognizant of the composites you're using, the conductivity of the gaskets and the sealants and the gap fillers. So it's kind of much wider, kind of a broader selection of materials that kind of come under this. Carl, I'm just doing a quick check because all I can see is my presentation. You can still hear and see everything?
Yes, we can still hear and see everything.
Okay, good. So, why did they change it? What we have here is a galvanic series, and I have seen so many versions of this type of information in standards around the world, where they stack up like potentials. They put these materials on a potential scale, yeah? And the thinking behind it is, oh, well, the further apart they are from this on this potential scale, then the more corrosion. Now, that will be indicative of risk of corrosion, but quantitatively, it's not, and scientifically, it's not exact. It's not really giving you information related to the kinetics of the corrosion. And if you recall on that F18, the bushing material they were choosing for the F18 was a stainless steel. Stainless steel, that's good. That won't rust. Let's do stainless steel. So stainless steel on its own, good. But if it's in a galvanic couple, it can end up being really bad. So if we look at aluminum on this potential chart, and we pick roughly where the stainless steels are, and you go, oh, there's a potential difference. And then you say, okay, what if we want to use titanium for our fasteners? Oh, no, that's not a good idea. The potential difference is larger. But if you look over to the right, if you actually make these couples and you measure the current between them, which is proportional to the corrosion rate, you find that for stainless steel and aluminum couples, the corrosion, the galvanic current, is much, much higher. So, you can't really have a standard that's driving you in this wrong direction. So that was like the impetus behind it all. And, and this is what they were seeing in reality. You get a test coupon or you look at a real system. We have titanium fasteners here on an aluminum plate, and we have stainless steel fasteners, and it's actually corrosion of the aluminum plate is accelerated by the presence of the stainless steel. And now the standard has changed, and if you use the polarization curves, you can do 3D calculations of this corrosion and calculate this map. And I'm going to show you a couple of tools that have developed from this. So military standard 889D doesn't use potential anymore. It is a requirement to calculate the corrosion current, and they do this through the polarization curves. So what they did now is pre-calculate, measured polarization curves for all these materials. This is in the standard, and it's just like in the old days before sat-nav. If you wanted to know how many miles between London and Manchester, you would pick one town on the left and pick a town on the right. What we've got here is all these numbered materials are repeated across the top. So I have aluminum 7050, I've got Ti 64, and I've got pH 15.5. And we just look across here for the 7050, and then we drop down with our expected couple of the Ti 64 and our expected couple of the pH 5. And you'll see these categories. Category 2 for the Ti 64, and over on the legend, you've got the mils per year range. This is a linear range. You have to look out for that. So now, this is in line with reality. Problem: the day this is printed is the day it's out of date. And anticipating that, in the appendix to this mil standard, they we helped with this piece, defined a protocol for measuring that polarization data. So if you have a new coating, because new coatings appear all the time, there's a process by which you can measure that and then combine it with the data available here. So, there is a way of continuing. So what we've done over the last few years, that was quite a few years ago, we created a SaaS software, corrosion. It has all of that data in there, and it has data for different environments. So what this essentially does is, using mixed potential theory, if you have the polarization curves of two materials in your couple, then crossing the anodic of one branch with the cathodic of another branch will give you that corrosion rate. So that's our starting point. And then we incorporated this capability into a CAD system. So in the CAD system, the CAD will automatically look for all of those interfaces and apply the mixed potential theory to all the materials either side of the interface and come up with a color code table of your corrosion risk inside of that CAD file. Then if there's anything risky in there, you can change the materials within the CAD system. If that doesn't remove it, maybe you need to do a redesign, and then there's a way of looking into the details. So you can import the 3D CAD into your CFD solution, and we can solve for the corrosion rate. And you can get a corrosion rate map. So you can see the gradients as it changes from high to low corrosion rates over your assembly. Now, one problem in terms of when you think about the people that use these, do you teach your materials people about corrosion? Teach your materials people about simulation, or your simulation people about corrosion? And for the materials and process engineers, we also produce kind of a middle ground here where you could put in dimensions, and there's a certain number of templates that can be picked. And very quickly, this is all automated for certain fixture systems. I'll show you that in a minute. So what you can do is you can go to like corrosiongin.com, for example, and you can look at all the material information. What we have, you can see, is quite extensive. And that can be added to because there's this protocol for gathering that data. So you can look at like substrates and different coatings, and you can play with this yourself for a selected number of materials. But essentially, we choose an environment. We have the mill standard environment, which is in artificial seawater, or we have a 3.5% sodium chloride environment, which the Navy were interested in. And this is like a requirement. So early on in your design, you can choose aluminum, different kind of versions of it, different tempers, whether there's a treatment, whether it's anodized or not, how it's sealed. We have curves for many of these different options. And then like the stainless steel here, the 13.8 pH we chose here, you run it pulls the polarization curves, and then it has a summary underneath here. So it will tell you what is anodic, it will tell you what is cathodic, you get the self-corrosion rates of each of the materials as well. And the big kicker, of course, is even though you can have a self-corrosion rate here that's really, really low, in isolation, when they're together, you got 497 microns corrosion, very corrosive couple. And so you can quickly copy that group. It self-populates, and then you can say, oh, no, this time I'll try titanium, and then you can put in zinc nickel, and you can very quickly go through those options. So in a very short time, I've just got a summary of it here. I looked at aluminum. I'm thinking, stainless steel fasteners or some part of my structure. Aluminum with Ti-6-4, like we talked about earlier in the Navair example. And you can see very quickly what that corrosion rate is. So you get a quantitative number, and it also reports the mill spec number as well. Now, maybe it's cheaper to just coat your fasteners, like a zinc nickel coating, a sacrificial coating. So here it's swapped around. So now the aluminum has become cathodic, so it's not corroding. That's a good thing. And the corrosion rate is really kind of a consumption rate of your zinc nickel. So you can see how you can do that pair by pair, and it's still quite, it's fast. But if you have a CAD system with your bill of materials with all the coatings already assigned, which can be done, then you can just, within that CAD system, just press a button and it will tell you it'll give you a table down here and tell you what the corrosion rates are. So, this is the way it can be deployed. So very early on in the design process, you can choose your environment again. You can just choose a few fasteners or a subsection of your geometry, or you could choose a whole geometry. And you just press do calculate corrosion, and it's really automated that mixed potential theory, that application, and applied the mill standard way of assessing corrosion rate. So it's great because then you can home in here on the piece that may be causing you issues. You could just do a change of coating on the fly. We're looking here at the difference between 15.5 pH and whether we passivate it or not, and you can halve the corrosion rate by just passivating it. Well, you can halve the consumption of the surrounding zinc nickel by passivating that stainless steel piece. Okay. And then it's really good that now they've decided that polarization curves are needed to get a more accurate handle on the corrosion rate. You cross the curve and you're just using a fraction of that curve where that intersection point is when you look at that table of pre-calculated corrosion rates. But if you use their polarization curves as boundary conditions in a 3D model, you can simulate and solve for potential and current density. It's kind of like, temperature and heat flow. You can actually solve for that and you can get the corrosion rate on all your different materials. So very quickly, what we did was we realizing the aircraft of like Meccano set. It's made of many different repetitive geometries, but joints, lap joints, and so on. And we created these templates. So now the AMPP person can put in dimensions. The geometry is automatically created. The computational mesh is automatically done. The solving is done, and they get to the actionable information, what those corrosion rates are. So that same data is being leveraged and deployed again, but now into a 3D framework. So we're using computational fluid dynamics, but we also solve now for corrosion rate. So we can read in our database all those polarization curves, and it's available actually within the software, so you can set up your design tree. We have surface materials here, and here you can see that Corrdesa database with the coatings and substrates all available just to be quickly assigned to those surfaces of the geometry that you're considering. So like the workflow can be, let's look at the structure. It's very complex. Let's get down to the body in white. That can be a mix of different materials. So the different materials can be assigned. That will flow through from your BOM. Press a button and you get all these corrosion highlights. You might be able to fix them by changing materials, deciding to coat it or coat it with a different brand of coating. Some things might need more of a deep dive. So you have this table, you can say, okay, let's look at these couples here and zoom in on them, create your 3D model and do a deep dive. So now, rather than just numbers, maximum corrosion rate, we can see how that corrosion rate actually flows and changes. Yeah. So we've got like risk on the left and deep dive, what's the actual corrosion rate map on the right. And it could be higher or lower because now we're capturing the actual geometry. So anode cathode area ratio of 1, it's not an assumption anymore. We have that geometry information. So although, the corrosion rates were higher in our risk analysis, they all trended in the same way. So in our risk analysis, we got a high corrosion rate, but it's just telling you where the risk is. But then you take in your 3D model and you solve for the current density, it ends up being lower because of the different areas and shapes of those components. But I find the simulation bit, try and figure out shift left, do more and more in the design. I just thought it might be interesting to touch on some of these. Sometimes you might want to change the coating. How are you going to do that on an asset that is already out there in the field? And I thought this could be interesting to some of you guys. If you're familiar with selective plating, it can be very messy. You can flow your electrolyte through here. You electrically connect what you're plating, the workpiece, to your electrode here. Flow the electrolyte through, and you can locally plate. And there's a non-drip process that does this. So we leverage this non-drip process. It's really quite interesting. They didn't believe it was non-drip on the side of this very expensive sub-hunter. It's a P8. But we did an anodized process actually on the plane. It came into the depot, we fixed it, and then it was out on patrol. So in terms of readiness, it was spot on. And I thought it'd be interesting to tell you a little bit more about those processes. It's interesting with the electrolyte is supplied to this tool through these little holes here, and then there's another pump that creates a vacuum that sucks back that fluid. And it just soaks this porous material just enough for it to be wet and complete the circuit. And then you move this tool about on your workpiece. That's essentially how it works. And what we did was we packaged this. There was a lot of things that we had to do. The idea was to bring this to the flight line. So it had to be very robust. It goes on aircraft carriers. It had to withstand, rocking around on ship and so on. But essentially, this is sold all around the world now. The F-35 use it. So we're only a small company. We're very pleased about this. And you can do plating actually on the airframe. So now we've been training people all around the world. We've trained over 100 people on this use, and we use this also in the UK. Okay, so we've took this further. So what we did then was develop a system using the same non-drip approach, where there's actually corrosion. So this is a U2, just an old spy plane, a lot of corrosion on there. And we developed a way to remove that corrosion, replate the fasteners, and reanodize the damaged aluminum around the fasteners. This is more complex a process, so we're putting a computer interface there because we're doing an electrolytic strip with one tool, and then we stop. The computer tells us when to stop. Then we do an anodize. You anodize the aluminum, and that essentially masks the around the fastener. And then we do a zinc nickel over the previous cadmium or bare fastener, and then passivate and seal and rinse, all basically on a mobile system. Computer controlled, because you have to walk the technicians through this. Also, being in the military, the technicians are often stationed there for only 18 months or 2 years. So there's a lot of churn as they move around. So you have to have a system that people can quickly get to grips with. But the thing is, it's always been a small tool. You can just do small repairs. And we did a lot of research, and over a year ago, we eventually managed to solve the challenge of making larger tools, but yet non-drip. So you saw the movie there where we're working on that static port here on this P8 Sub-Hunter. That was our demo. And now we've created larger tools where we can do much larger areas of anodizing repair actually on the asset, on the aircraft itself. And we're taking this to larger aircraft, C5, that's a Galaxy, it's really big. And in the, it's huge. You can walk in there, you can fit 2 tanks in there. You can fit a helicopter in there. And you can even play tennis in there. It's big enough to play tennis. Also, it's interesting from stern to the front of that plane. It's longer than the first ever powered flight by the Wright brothers. So they could have completed the takeoff and landing within the length of this plane. And what they have with all this equipment, the floor gets damaged, and this in-tank anodize is really tough. And when they put a patch on, there's a standard repair for putting the patch on. They damage the anodize because they have to adhere the patch to the floor. So the anodize gets damaged, and they wanted a way of repairing that, and that's what we did. We created a repair for that. And also, they had another issue on the plane, on the wing plank. There are fasteners that cannot be removed. So that was a problem. How can we fix these corroded fasteners in place? And again, this is like a huge wing. You can play cricket on there if you decided to, although you have to be careful. It's pretty high. Anyway, so what we did then was it was similar to that U2, but we've got larger tools. So you can see the corroded fasteners here. We've stripped the cadmium off there. If there's any left, it's often completely gone by then. We can't coat with cadmium. It's possible to do it, but of course, low hydrogen embrittlement zinc nickel is now what we're replacing it with. And then reanodize the aluminum, because what they found that in removing the corrosion, the technicians essentially were putting abrasion material on the end of drill bits and damaging the actual plane as well. So here you have corroded fasteners. This was a test, and after doing the stripping, replating, reanodizing seal, it was colored so that we know that it had been reanodized. The pristine here. So this can all be done actually on the aircraft. So a couple of years ago, despite all this development, you have to denval it, do it on the aircraft, and that's exactly what we did. We created this equipment, we tested it on real pieces in the lab, and then we actually went on a C5 Galaxy during the repair process, did the prep in situ, the anodize, the seal, and we have a complete repair, checking the integrity of the repair. So now the standards, the tech orders are being changed in order to accommodate this solution of anodize repair on the asset. Back to the software, I could just point to a couple of future capabilities that might be interesting. You put data in, you get results out. It's very deterministic, isn't it? So what we've done, rather than assume a 24/7, 365 time of wetness, let's look at the weather data. So now we have a tool that reads in the weather data and applying an ISO 9223 where condensation is expected above 80%. We can march through that, and we can look at the impact of what that corrosion rate would be depending on where that asset is stationed. Okay, so interestingly, the standards to wash the airplane were based on where the airplane is based. So for a fighter or trainer, which is quite local, that's fine. But if you have a cargo plane like that C5, then it can spend a good part of its time in the Indo-Pacific, Guam, and so on. So here we have Lancaster, not England, Lancaster, California, much drier. We've got a corrosion rate here, 4. And then if we use the same geometry, it's just a test geometry, the corrosion rate can be like 5 times more as a consequence of this weather. And now we're looking at degradation of top coats. We have a technique for acquiring data on organic top coats. And we can insert this experimental data into our model so we can look at the degradation of the top coat, then the ensuing galvanic corrosion of the inorganic coatings, the galvanic corrosion of the inorganic coatings underneath. And even though all these different coatings follow the same spec, they all performed widely different. Our lab technique that we've developed ranks them in the same way. We do it in a few days rather than a very long time. And if you can then incorporate that data and apply it on your new 3D plans for the next bomber, the next air taxi, whatever, then you can see how well your system performs. So to conclude, the standards changed. They went from a potential series to calculating the galvanic current. That essentially means the use of polarization data. So this mixed potential theory, so you can get a much more accurate handle on corrosion rates between galvanic pairs. We incorporated that to automate it into a CAD system, so you could do it over, hundreds and thousands of interfaces automatically. And then we incorporated the polarization curve database into a 3D solver. And inside that CCM plus solver we used, we can calculate the corrosion rate over these, it doesn't take long before, 2 or 3 coatings and multi-material, multi-body assembly, it soon gets quite complex. And I think this is the approach to adopt. And I showed you how we can locally plate and anodize and also strip corrosion, and many more processes can be mobile and non-drip to take right to the asset. So, Carl, I'll wrap it up there and take any questions.
Excellent. Great work, Alan. It was good. I liked some of the facts that you were putting in there. 23% of failures in aircraft relate to corrosion. That is high.
Yeah, I'm quite surprised by that.
Yeah, we've got a couple of questions. I'll do them in order. So the first one came in from Tassos. It's just loading. How the Corrdesa model works? Do you identify / model severity of corrosion or estimate corrosion rates?
So what was the bit before you said or estimate corrosion rates? Do we?
Yeah. Do you identify / model severity of corrosion or estimate the corrosion rates?
Is it written down?
Yeah. Flip over to the Teams chat, and then it's in the Q&A.
There we go. How the Corrdesa model works to identify model severity of corrosion. What is the corrosion rate? Okay, so I talked about the polarization data. So polarization data, this is a nice way of looking at the galvanic corrosion because it's fast. We don't model the actual chemistry. It's possible to do that. We don't model the chemistry. We capture that information through this polarization curve. What's a polarization curve? It's kind of a function of the material and its environment. So essentially, you're limited to modeling, environments for which you got the data. So that's one thing, but it's very, very fast. So our database of all polarization curves are taken according to a standard. So we just have this single triangular matrix of all these polarization curves for different materials and coatings, according to a reference, saturated calomel. And so then we can compare one material with another. So it's not like fixed corrosion rates. The mill standard has done the calculations for you. And if you ran our gin, you get the same. But if you can use those polarization curves in a model, and the model solves the field of potential and the field of current density, then on the fly, and then uses those polarization curves as only boundary conditions, so you know what happens over the entire model. So, and then if you want to take into account like different severities, like for instance, these polarization curves we've taken in 3.5% sodium chloride at a certain temperature. We've taken polarization curves in 5% sodium chloride at a higher temperature to align with B117, because people were saying, we want to see how it compares with our accelerated chamber test. So you have to take the data in the environment of choice. So if you have a more aggressive, more severe environment, then you need to have the data that has been taken from there. But then you have the fidelity. You calculate that corrosion rate over the entire geometry, and it'll go up and down according to recesses and pointy bits and whether the sacrificial coatings are. All that is taken care of in one shot.
Mm-hmm. Thank you, Alan. And then it probably segues to our second question, which is actually in the chat rather than the Q&A. This one's from Ling Hao.
Okay. Okay, yeah, so you can use polarization curves to quantify galvanic corrosion. So that's kind of missed out there. But if you've got the polarization curves and you're looking at the interaction between different materials, you can look at the interaction between these different polarization curves that are set for each and every surface in your 3D model. Okay. If there's no galvanic corrosion, then I guess it backs out to more like your stealth corrosion, your uniform corrosion rate. If you recall, in that table, we had the galvanic corrosion, but you also had the information on the uniform corrosion rate. It's, like I said, the big thing for the Navy was galvanic corrosion. So we did that first. We've done some modeling of pitting corrosion. I think as an engineering approach, my personal opinion would be to maybe go with a kind of a risk of pitting, because if I've got pitting, I've got an issue already. Do I care if I model it to the 10th decimal point? That's, as an engineer, that would be my approach. So we're working on a kind of a risk model, the propensity of pitting based on science. These are physics-based models, so that's a good thing. Crevice corrosion, a combination of geometry and shape and also a varying local environment between the bottom of the crevice and the top of the crevice. As an engineering solution on a total assembly, like a whole wing or a plane, it's difficult to deploy. You can have an idea from experience of where you might have corrosion. So it's not in this, but we can model crevice corrosion. But are you going to model each and every crevice in an assembly of thousands and thousands of components? So it is possible to model crevice corrosion, but not in the context of the models I shared with you today. Polarization curves are applicable. Hopefully, that finishes. That addresses that question.
Yeah.
Any add-on to that?
There's one final question from Tatos again. Is a free demo version of Corrdesa model available?
Yeah, so let's have a look. I think I got it. Okay. So go to the corrosionchain.com. It's here. And like I said in the movie, I kind of rushed through it, but yes, you can kick the tires. You click on materials.
Sorry, if you're sharing your screen, Alan, we can't see it.
Good reminder. It's not a secret. Here we go. Yeah, so if you can see, I'm in my browser, corrosionchain.com.
Mm-hmm.
And you click this materials, we have substrates coatings. You can click on them and you can see what we have. You click on the individual coatings, you won't get much information because that's encrypted and for users. However, it's interesting to see the extent of our data. But if you go to the galvanic corrosion risk analysis up here, you can select an environment. At the moment, we just have the mill standard. And you can go, we have just a few materials, active aluminum, more noble titanium, just so that people can kick the tires and so on. So that's our immediate go-to if you want to give it a go. And then, if people want to kind of do calculations with the bigger database, we can evaluate it, and there's other ways of moving forward. But I found this very useful. Yeah.
Perfect. Thank you, Alan. I've put the web address in the chat as well for people, corrosiongin.com. Did you also want me to put your email address in there if people want to reach out to you?
Yeah, please do that. Happy to do that. You got that, rose@corrdesa.com.
Perfect. I don't think there's any more questions. Just want to thank the people on the line for joining us, and thank you for your time, Alan. I wish you safe travels on your way north, during your road trip around the UK.
Yeah, thank you very much, Carl. Thank you all. And any questions, just reach out to me.
Fantastic. Thank you, Alan.
Okay.
Take care.
Holiday. Take care.
You too.